Question 21, we have a cyclic compound there. We heat it up with dilute hydrochloric acid. Well, I can tell you that this is an amide. That is an amide. So we can hydrolyze the amide there. And we also have a different functional group here. This is an ester. And we can also hydrolyze ester in the presence of acid. So what you get is you get acid hydrolysis in the presence of dilute HCl, and you do reflux as well. We're going to get OH. We're going to get carboxylic acid like that. And we're going to get the carboxylic acid there. We're going to get NH2, which by right, in the presence of an acid, I don't really stop at NH2. Instead, what I get is NH3 plus and Cl minus. I get a salt because amines are basic. Therefore, in the presence of acid, it's going to protonate and give me a salt there, which is why the answer cannot be the free amine. This is free amine, and free amines are basic. You have lone pairs on the nitrogen, and this is under acid hydrolysis. So we do get the salt. And here is free amine again. So A and C is out. And we just need to look at the correct product here. This one, if we read the skeletal formula, is HOCH2CO2H there. HOCH2, well, this one says it's an aldehyde. We do not get an aldehyde upon hydrolysis. Therefore, this must be wrong. Therefore, D must be wrong. And B is correct there. You can see that this is basically that written in opposite order. You just read from right to left. HO2C, CH2OH. And then this one is just HO2C, CH2, and H3+. They don't mention the salt, which is basically the chloride salt. These are not bonded directly by covalent bond. These are bonded by ionic interaction. Question 22, you have a large number of polyunsaturated. Poly means many. Unsaturated means you got carbon-carbon double bond. It could also be carbon-carbon triple bond. But that is less likely since that one is not really directly in your syllabus. And these are carboxylic acid, so you have CO2H functional group as well. When you use it to make margarine, and we know that we use nickel catalyst in the hydrogenation of alkenes to make margarine, and that is a heterogeneous catalyst. And you learn about heterogeneous catalyst under rate of reactions, where the nickel is solid, and then these are hydrogen gas, and then these are high temperature, and then your alkene there is going to be different phase from this solid. They're not going to be solid as well, the alkenes, and that is why there is heterogeneous catalyst, because the catalyst is in a different state, different phase from your reactants there. This is catalytic hydrogenation, which is essentially high temperature, the presence of the hydrogen gas and the nickel catalyst to help speed up the rate of reaction. Question 23, which one forms in the greatest amount? They want the intermediate ion, and this is addition of HBr to propene. So you know this is electrophilic addition mechanism. If I draw out, it's better because you see what is going on. So always attempt to draw out and see it for yourself. It's very rare that I draw a display formula, but I'm just going to draw it here so that it's clear. The first thing I do is label dipoles. Now from the lone pair, not lone pair, but here you have very rich electrons in the pi bond. From the pi bond, rich attack poor, and then heterolytic fission. As stated in the syllabus, heterolytic fission, the movement of two electrons there. Now my hydrogen could add there, and I get a positive charge there, or my hydrogen could add here, and I get a positive charge there. That's why I have to think about the two different carbocation. So I'm going to add the hydrogen there first. Doesn't matter, I get a positive charge there. Now what is the other possibility? Well, the other possibility is when the hydrogen add to the other side, then I'm going to get carbon, carbon, carbon. I will get hydrogen there and hydrogen there. H, H, H. And I get two hydrogen there and I get plus there. Now what is very important is it could be this or this. Actually it's this and this because they are possibility. But one of these is more stable than the other. You have to consider where is the carbon with the positive charge. The carbon with a positive charge is bonded to two other carbons. This is what you call a secondary carbocation. This is about stability of carbocation intermediate. As stated in the syllabus, candidates should be able to explain the stability of carbocation in terms of the inductive electron donating effect. So this is a alkyl electron donating group. This is an alkyl electron donating group. Secondary carbocation, 2 alkyl electron donating group to stabilize the carbocation. The carbon with a positive charge is only bonded to one carbon. This is a primary carbocation. You only have one alkyl electron donating group by inductive effect. So I can say that secondary carbocation is more stable than primary carbocation. Therefore, this will give me the major product where the bromine is there, and that will give me 2-bromopropane, which is the major product, and the 1-bromopropane, which is the minor product. So I gotta look for the correct one. Anything with a negative will be wrong. For electrophilic addition, I get a carbocation intermediate. The primary carbocation there is less stable because you only have one alkyl electron donating group. The more alkyl electron donating group you have, by inductive effect, that can donate electrons and stabilize the positive charge. By the same argument, tertiary carbocations with 3 alkyl electron donating groups, because the carbon with a positive charge will bonded to 3 other carbon, will be more stable than the secondary carbocation, which in turn is more stable than the primary carbocation there. Question 24, so this is an amine. You can see that this is an amine because this is an NH there, is carbon and carbon there, it's not a carbonyl. And we have this ammonia reacting with this thing, but this is cyclic, so how do they click together? So it can be thinking about, breaking it up there and there. So what we have there is going to be Br, then we have NH like that. So I'm just simply working backward, and then we must have Br there, and then CH2. Let me just complete the whole story, but I need a bit more space here. CH2, CH2, CH3. So nothing has changed except for these Br and Br there. So that carbon is still that carbon there. So this is 1, 2, 3, 4, 5, 6, 7, and 8. That thing is going to be carbon 1, 2, 3, 4, 5, 6, 7, 8. And what happened with the nitrogen there is this nitrogen loses the H there, because that thing going from right to left, that thing is going to do nucleophilic substitution. You have a halogenoalkane, so delta minus delta plus. You have a lone pair on the nitrogen, so delta minus delta plus on the CBr again. The lone pair on the nitrogen can act as a nucleophile, and then they attack there, and then you're still going to get another lone pair back again after you lose the H plus, and then there's going to attack the other side and close up the ring. 2 times nucleophilic substitution, and you will kick out 2 times HBr there. You want to know what is the name of this compound X. So X is basically the starting material here, excluding the NH3 of course. Well, we have minimal number, the smallest number on the halogenoalkane, rather than going this way around, which will give me number 8 for this bromine. Not good at all. This is correct. Bromine at position 1, bromine at position 5 is a 1,5 dibromo, and I've got 8 carbon in the longest chain. Octane, 8 carbon in the longest chain. D is the only correct answer there. Question 25, we have 2-bromopropane. This is hot concentrated sodium hydroxide in ethanol. This is not in water. If you don't have sodium hydroxide in water with a halogenoalkane, this is not hydrolysis. Hydrolysis is in the presence of water. This is in ethanol, therefore this is elimination. This is elimination of hydrogen halide from halogenoalkane. Very important case study. Hydrolysis versus elimination. You can catch more of these in my topical playlist on halogenoalkane chemistry. You want the major product, so let's have a look at this. This is 2-bromopropane. So you have a hydrogen on the next carbon, but this carbon and this carbon there, they are symmetrical about the central carbon, so it doesn't matter which one you get or which hydrogen you remove. You can remove like that, or you can remove like that, but that and that is exactly the same molecule. It's not like major and minor, it's just one same molecule. We're gonna get is 1, 2, and 3, 1, 2, and 3. So it's the same product name, pentene, pen1-ene, okay? Oh, sorry, not pen, but prop1-ene actually, or propene. You don't get the alcohol because these are hydrolysis product, and hydrolysis product is favored by hydrolysis conditions, this is favored by NaOH aqueous. That means in water, not in ethanol. Okay. And these two hydroxypropenes, you don't get that as well because you just do elimination and not hydrolysis there. So D is the best answer. Question 26, we have the presence of a halogen and we detect it by heating it up with aqueous silver nitrate. So the presence of the water will do hydrolysis. And when we do hydrolysis, we are concerned about breaking the weakest bond of all. We know that going down to group 7, so carbon fluorine, carbon chlorine, carbon bromine, and carbon iodine. Going down that group 17, or the halogen group, we know that the halogen gets bigger. And when the halogen gets bigger as a result of more electron shells being filled, and that means that the covalent bond become longer. And you know that in the bonding topic, a longer covalent bond means that the covalent bond gets weaker. And when the covalent bond gets weaker, it's easier to break, easier to hydrolyze. And that is why anything that has the weaker bond will be hydrolyzed first, and the quickest to produce a precipitate will be something that contains like carbon iodine bond. Out of all of these, this is the only one that has carbon iodine bond. So the rest doesn't matter how many CF bond you have, as long as you have one of the CI, that is the weakest. And that means the weakest bond will hydrolyze first, and when you break that, you're going to generate I-, which is going to precipitate out with the silver nitrate to give you silver iodide. You will see a yellow precipitate, which is AgI. So a yellow precipitate will be the first precipitate to be observed here. Question 27, which one will give you a different observation? So a different observation could mean a different reactivity. What we have here is this carbon with the OH. This carbon with the OH is bonded to one other carbon. This is a primary alcohol. And this carbon with the OH for X there, this carbon with the OH is bonded to 1, 2, and 3 carbons. So this is a tertiary alcohol. So in terms of the two alcohol reactivity, both of them will react with hot SOCl2. This will turn the alcohol into halogenal alkane. You substitute the OH with the Cl, and what happened then is you kick out SO2 gas. You also kick out steamy white fume or HCl, hydrogen chloride, steamy white fume there. So RCl, when the Cl goes there, the H goes there, and the oxygen combined with the S to give you SO2 there. This is a general equation to show alcohol converting into halogenal alkane with the use of SOCl2. They do ask you this question in structured paper, not just in A-S, but also in A2 paper 4 as well. For this hot acidified dichromate 6, this one is only for alcohol that can be oxidized, so primary and tertiary alcohol, but then X is a tertiary alcohol. Tertiary alcohol is not oxidized. That is because you do not have a hydrogen on this carbon there. So no hydrogen on that carbon with the OH, and therefore you can't lose what you never have in the first place, and therefore you cannot reduce this tertiary alcohol carbon there. So B is actually going to be the answer we're looking for, because it will react with this primary alcohol, it will oxidize the primary alcohol, you will see orange to green coloration. So this orange color is the chromium plus 6 in the dichromate oxidizing agent. It has to be acidified for it to work as an oxidizing agent. You're going to get a green coloration, chromium plus 3 oxidation state, chromium 3 plus aqueous. That is the final state when this dichromate 6 acidified acted as an oxidizing agent here, but this one will remain orange because the oxidizing agent does not oxidize tertiary alcohol. That's why this is the answer. Give you a different observation that NaOH will react with both alcohol, and if you have alcohol and you react with sodium, you're going to get sodium alkoxide. This is as stated in the syllabus, and you will get hydrogen gas similar to water adding with sodium, going to give you sodium hydroxide and hydrogen gas, balancing the equation there. Warm Fehling's reagent, this one is only going to oxidize aldehyde, and if you don't have aldehyde, that means you don't see any silver mirror. Silver mirrors with tolerance. This is Fehling's, so the solution will remain blue for both W and X because there is no oxidation of aldehyde happening with W or X since there's no aldehyde functional group there. Question 28, we have Ledenberg, who suggested a structure for benzene. C6H6, you learn more about this in A2 chemistry, but this one is just saying a compound here, C6H4Cl2, could be formed with the same carbon skeleton. But you have 2 chlorine. Instead of 6 hydrogen, you have 4 hydrogen and 2 chlorine. Where can you put the chlorine? How many structural isomers can you have? Well, let's see. If I have a chlorine there, and if I have a chlorine there, that is 1 isomer. And I'm just thinking, if I have any of the chlorine on the other side, that will be the same, I guess. So like that, and then a triangle like that. What can I think of here? So another one would be 1 chlorine there, 1 chlorine there, so there's 2 already. But because of the rigid structure, so you're gonna have something that overlaps, you know, the triangle in front, the triangle at the back. If you look from the central axis there, so if you have chlorine and chlorines, they can be rotated about the center there. So as soon as you have 2 chlorines on this one plane there, it's going to give you the same structure. If I have now this one, so one of the chlorine is like that, and the other chlorine is like at the back there, so I'm using a blue color there. No, I don't want that, do I? Okay, I think of another one actually. If you are on the same phase, if you have chlorine and also chlorine, I'm wondering if you can have chlorine and chlorine, but you can't have that because 1, 2, 3 there already, so you cannot have carbon with 5 bonds, so that is actually impossible. So I can't have the carbon, 1 carbon there forming 2 chlorine there, so it has to be 1 chlorine at the back there. So what I'm saying is like this, 1 there and 1 there, and I can imagine if I just copy this, you can hopefully, I meant to copy that, and you can hopefully see that when I move this around, it's going to be different because I cannot rotate this freely, unlike when they are here, I can rotate about freely. So this is the same as when you have 2 chlorine there, like that. It's the same as having 2 chlorine there, like that. But this thing is different because this is on the top face, this is on the bottom face. So that is going to be 1, that's going to be 2, this is going to be 3. And the last thing I can think of is whether this is the same as that or not. So something you have to consider where this thing is on the next carbon. So let me think, is that the same or is that different? That would be actually the same as number 3 if you follow the thing there here. So here you can do like that, that is 1 and 2 like that. So here I can go 1 and 2 like that. So again, they are symmetrical about this center position here if I draw this correctly, like that. So and then I draw down the plane there, so that is like that. So there's the plane in which they're symmetrical by. So when the chlorine is there, when the chlorine is sticking out at the back there, it doesn't really matter because these and these are the same. So this is the exact replica of number 3 there, and not of number 2, because when you go to number 2, what you have there is the chlorine are separated by 1 carbon only, like that. Okay, and the same thing there, the chlorine are separated by 1 carbon, but they are on the same phase there. So altogether we have 1, 2, and 3, and it's all about rotational symmetry. Question 29, we have the citrus flavor of lemons due to this thing called limonene. And what do we have in limonene? We have alkene, and we just have alkene on the other carbon as well. So what is the mole ratio of carbon dioxide to water? Carbon dioxide to water when you're completely burnt. So this is in excess oxygen. So that means you have enough oxygen, you're not going to get carbon monoxide. So this is about balancing equation, I think. So just read the skeletal formula. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 carbons. And now we're going to read the hydrogens. So carbon form 4 bonds. We don't show the hydrogen bonded to carbon. So there are 3 hydrogen here. This is the CH3. Carbon form 4 bonds. Group 14 with 4 valence electron. Carbon here from 1 bond. There are 3 hydrogen which are not shown. Carbon from 4 bond. 1, 2, 3, and 4. So there is 0 hydrogen there. Carbon from 4 bond. There is 1, 2, and 3 there bonded to carbon. So there's 1 hydrogen. Carbon from 4 bond. 1 and 2. So there's 2 hydrogen. Carbon from 4 bond. Carbon here 1, 2, and 3. So there is 1 hydrogen. Carbon from 4 bond. There is 0 hydrogen. Carbon from 4 bonds, there's 3 hydrogen. I think you're sick of me saying carbon from 4 bonds already. So carbon from 4 bonds, 1 and 2. So there's 2 hydrogen there. Carbon from 4 bond there. Carbon from 4 bond there. So there's 2 hydrogen and 2 hydrogen. And I think that is pretty much everything. So we're just going to add out the hydrogen now. So 3 plus 0 is 3 plus 1 is 4. 5, 6 plus 1 is 7. 8, 9 plus 3 is 12 plus 0 is 12. Plus 2 is 14, plus 2 is another 2, so there's 16. So C10H16 plus O2, giving me CO2 plus H2O. Reading your skeletal formula correctly, you get 10 carbon, so you get 10 CO2. Am I correct? Why am I getting this one wrong? Okay, so there is 10 CO2, but we have to work out the ratio of the H2O first of all. So when I balance the equation, there is 16 hydrogen, so I need 8 H2O. Having said that, I have 10 times 2, which is 20 oxygen, plus 8 oxygen, so 28 oxygen, so that's 14 O2. I want the ratio of the moles of CO2 is to the mole of H2O. Simplest ratio, 10 is to 8, divide by 2 both sides, you get 4 and 5. So there's 5 mole of CO2, and that is to 4 mole of water. That's the simplest whole number ratio based on this complete combustion. I'll give you CO2 and H2 only by reading the skeletal formula of this alkene correctly here. So not C30, but question number 30, when you have ethanamide. So this is an amide, and as you can see, this is a CH3, and it's bonded to C double bond O. There is an NH and an NH. This is a terminal amine. That's why it looks a bit weird instead of the usual CO2H. CONH, and then an R group. Here it's just hydrogen. So what we're going to do is we're going to hydrolyze this. And when you hydrolyze it with sodium hydroxide, this is a base hydrolysis of amide. We need to be careful. One of the products that we expect to get will be a carboxylic acid, but you are doing base hydrolysis. So this left hand side is the carbonyl group. There is actually the carboxylic acid group, and on the right hand side that comes from the amine group. As I mentioned, you are expecting a carboxylic acid, but you're in the presence of a base because you're doing base hydrolysis. Just like in base hydrolysis of ester, you're not going to get the carboxylic acid. Instead, that's going to be deprotonated and neutralized to give you the sodium salt because you're using sodium hydroxide. But the amine itself is basic, so it doesn't have any effect in the presence of this sodium hydroxide. So what we get is the salt as well as amine. There is no amine in the product. We do get salt, but we get a carboxylate and not an ammonium salt because this is in acid hydrolysis. If you use sulfuric acid or if you use hydrochloric acid and reflux for the acid hydrolysis, you're going to get B. So you don't get B, you don't get A at all. Instead, what you get is D there because there is the hydrolysis product, the carboxylic acid getting neutralized, getting deprotonated by the base in the condition here, base hydrolysis of not of acid but of amide. Don't know why I wrote down acid there. Okay.